Okay, we're going to do a little bit of a review going through some of the equations that are involved in Newtonian gravitation and also Kepler's third law. So we have a picture of the Earth and the Moon and a satellite here. We have the distance of the Moon from the Earth, which is from the center of the Earth to the center of the Moon. We have a satellite right here, which is telling us it weighs 1,500 kilograms, and it has a period of 21,600 seconds. Okay. We also, the Moon, we are told the distance is 3.84 times 10 to the 8th meters, and it has a sidereal period of 27.4 days, and that's roughly 2.348 to the 10 seconds. So what do we want to do? Well, we want to figure out a few things here. Here are all the parameters that we are going to be working with. So I kind of went through these, but we can see I'll be making a photo of these so you can refer back to them. But these are the mass of the planet, and this is actually the planet Earth. Okay, mass of the Moon, our Moon, mass of the satellite, radius of our planet, the Earth right here, distance from the planet to the Moon, 3.84 times 10 to the 8th, the radius of the Moon, which we may use if we want to find the acceleration of gravity, the period of its moon, which is the Earth's moon, is 27.4 days, and we're going to use a satellite that's actually orbits. One orbit takes 6 hours around the Earth. And what we want to do also is to find the altitude of that satellite at that height. Okay, so Newton's law of gravitation, force, is basically about if you have two masses that are some distance away, and we can call that distance just r, and it's from actually the center of each, if you will, planet and moon, moon and moon, planet and planet. And he basically said that there is a force of attraction between the two. Now, this force of attraction is not exactly directed toward each other. What happens is they both travel around a common center point. Okay, for example, it could be here. Okay, and so this is the center of rotation of the two planets, and it's based on actually the mass. Of course, the heavier mass is going to be closer, the shorter distance from the center of rotation than the smaller mass. So if this was the moon, our moon, and the Earth. Now, you could find the center of rotation by taking the mass of, say, the moon, our moon, and the mass of the Earth. This will give you a ratio times the distance, we'll call that RD, the distance between the Earth and the moon, and this will give you the distance from the center of the Earth from here. So both the moon and the Earth are actually going around as they are attracting each other. This is going this way, and they're going around the center point. Now, the moon does go around the Earth in this case, but because of the short distance to the center of rotation of the Earth doesn't go around the moon. Now, what Newton saw through experimentation was that the force between two bodies was equal to some proportion of the product of both their masses divided by the distance squared. The question is that this was a proportionality, but it did not tell us what the constant was. He had to do it by experimentation. And it turns out that experimentation revealed that the constant was a universal gravitational constant, and it came out to 6.667 times 10 to the negative 11. It's unitless, and it's used in almost all calculations when we talk about planetary mechanics. So Newton's equation is a vector, g times the product of two masses, the inverse of the square of the distance, which is a vector. Okay, so let's take a look and find out what is this force between the Earth and the Moon. Okay, so first of all, we have 6.67 times 10 to the negative 11, that's g. Then we have the mass of the Earth in kilograms. And then we have the mass of the Moon, which is 7.35 times 10 to the 22nd kilograms. And all this was divided by the distance between the Earth and the Moon, 3.84 times 10 to the 8th meters. And this is squared. All right, so keep in mind though, this is from the center, this distance is from the center of our Earth to the center of our Moon. Okay, so we're going to take this equation and we're going to turn this into other things, like we're going to look at how to derive escape velocity, how to derive potential energy of, say, a satellite that's orbiting the Earth, and also we're going to show how Kepler's third law is derived. Okay, so let's get started with that. Okay, so the first thing that I'm going to do, let's write down our equation, Newton's equation of gravitation, is G, two masses, the product of two masses, divided by their distance from the center squared. Okay, and this is equal to a force. Now, this one, what I'm going to do is potential energy. Okay, so this is the gravitational potential energy. So if we have a satellite that is orbiting Earth, okay, it has a certain amount of potential energy due to the altitude it is at. There is also kinetic energy related to its actually orbital velocity, but that is different than this right here. This potential energy is related from the height it is at, but also incorporates both masses of the Earth and the satellite. Okay, so how we do this is that we have this equation here, which is the force, and what we want to do now is that we want to turn this into energy. And how do we do that? We know that force times distance is energy. So let's write that down. We can call this actually the work done is going to be equal to the force times some distance. Okay. In this case, we do have an expression here, an equation that does have force. And this d is this distance. This r is distance. So we can rewrite this into, okay, that force is dot r is equal to G M1 M2 and then R3 or R2, I'm sorry, and then R. Okay. So we have what? We have energy on this side, and we also have energy on this side. We can get rid of this square and cancel out that right there. And this all becomes the work done. Now, if it's conservative, then the change in kinetic energy is equal to the change in potential energy, or just potential energy. So this becomes potential energy. And because it has a potential energy that it will always be negative because of gravity. So negative G times the two masses only divided by R squared. Okay, so let's look at a problem where we have a satellite that has a potential energy, or I'm sorry, it does have a potential energy, but it's going to be, let's look at this right here, 6.67 times 10 negative 11. That's the universal gravitational constant. Okay, and the distance of the satellite that we're looking at is 0.67 times 10 to the 7 meters. Okay, and then we're going to take the mass of the Earth, 5.98 times 10 to the 24th kilograms times the mass of the satellite. Okay, and so this is going to give us a potential energy of 3.58 times 10 to the 10 joules. So the answer to this would be negative 3.58 times 10 to the 10 joules. And that would be the potential energy, the gravitational potential energy. Okay, so we saw that by taking Newton's gravitational equation, that we were able to derive the potential energy of the satellite in orbit at a certain distance, in this case 1.677 times 10 to the 7th meters, orbiting Earth. Okay, so now let's look at another derivation using basically almost the same method. Okay, so we have Newton's gravitational equation here, and this one we want to find escape velocity. Now, escape velocity is a velocity that a mass that is going to leave or wants to be able to be launched into space has to achieve this velocity. So we're going to see what that is for Earth. So first, I'm going to derive the escape velocity from this equation. Okay, now we know one thing for sure, is that when a projectile is launched from Earth, it has to go a certain speed, otherwise it will follow a parabolic curve and come right back down to Earth again. If it has enough energy, kinetic energy, then it has enough speed, it will follow the parabolic curve. But when it comes back down, it will miss Earth and it will go into an orbit. Okay, so we need to find what is this velocity that will do that. Okay, so let's take this equation. Again, we need an equation of energy, and specifically kinetic energy. So if you remember from the last example we had the work done was a force times R is going to be equal to G M1 M2 R. We don't square the R there. Okay, so this both sides of the equal sign are equivalent to joules or energy. Okay, and we're going to take this force times distance, and we're going to say this is going to be kinetic energy. So kinetic energy is equal to G M1 M2 R. Okay, so now I don't like just having kinetic energy there because I need a velocity. So what is that? So it's 1/2 mv squared, our kinetic energy equation, equals the gravitational, universal gravitation, the two masses multiplied, and the distance. Okay, so in this case, we have two masses, but we don't really need two masses because we're only talking about the Earth. So we can get rid of this mass right here. Okay, and so now we have 1/2 mv squared is equal to this. So all we need to do now is to solve for that velocity. That velocity is part of the kinetic energy equation, which if it takes so much energy to get out into an orbit, then this must be the escape velocity, okay? And so let's do that. So the escape, by taking this and solving for v squared, the escape velocity will be equal to 2, the gravitational constants, the mass of the Earth, divided by the radius. Now this R, which in this context here of the force, was a distance between two bodies. Now this is, because we only have a single mass, now it becomes the radius of the mass of whatever planet this is. Okay, so let's solve for what the escape velocity is of Earth. This is 2 times 6.7, sorry, 6.7 times 10 to the negative 11 times the mass of the Earth. Okay, and all this divided by what? The radius of the Earth, 6.38 times 10 to the 6 meters. Okay, and we don't square it. We do take the square root. Okay, and so doing our calculations, the escape velocity is going to be equal to 182 meters per second, about 11,000 meters per second. That is roughly 25,000 miles per hour. So when we launch a rocket or a space shuttle, it has to reach this speed for it to reach space and to achieve an orbit around Earth. Okay, so this is how we derived the escape velocity equation from Newton's gravitational equation. The next one I'm going to do has to do with the acceleration of gravity. Okay, the acceleration of gravity. How do we derive that? Again, we'll take Newton's gravitational equation, G m1 m2 divided by r squared. Okay, so using Newton's second law, we all know what Newton's second law is that force is always equal to ma. We have a force here. So let's equate this. Ma is equal to G m1 m2 r squared. Okay, now again, we have on either side an extra mass. We'll cancel that mass out and we'll cancel the second mass out because we don't need it. So now we have an equation that says acceleration is equal to the universal g, then times mass divided by r squared. So now this is the acceleration of gravity equation, okay, or also on Earth what we call g, okay. And so it is 6.67 times 10 to the negative 11 times the mass of whatever planet, in this case Earth, times 10 to the 24th kilograms, all divided by what? Well, the radius of the Earth this time again, 6.38 times 10 to the 6 meters, and it gets squared, okay? And you know what? When you follow this through and do your calculations, it comes out to 9.8 meters per second squared. So that is a derivation and solving the acceleration of gravity for planet Earth. The next one we're going to do is deriving and talking about Kepler's third law. Okay, so we're going to derive Kepler's third law. Okay, which basically says that a period, and we use t as period. Period is the amount of time it takes for, say, a satellite to make one revolution around a planet, say Earth, squared, is equal to the distance the satellite is from the main planet it's orbiting. In this case, we call this r, and it gets cubed. And this is the relationship that Kepler found of how the planets go around the sun, okay, and their distances and their time periods, okay. For instance, Earth, its period is 365 days. Its R is about 93 million miles, okay, and that relationship holds true for Mars, Jupiter, Venus, all planets. But how did we come up to this? Okay, well, to this point, let's go start again with Newton's equation. Okay, his gravitation equation. And let's just think about this for a second. Okay, so Kepler's third law is pretty much about a planet or a sun, and then we have some satellite or planet or going around the sun. Okay, and it has a period, how long it takes, and it also has a distance, okay? And the other two laws of Kepler, the first one is basically all orbits are elliptical, and the second one is to do with equal areas, okay? So you have an equal area here and an equal area over here. That what this means basically is that when the satellite is the furthest from its primary planet, it's going to go a lot slower. It's going to have a low V. And when it gets closer, it's going to start going faster. That's the second law. But we're interested in the third law. Now, if we look at anything that a mass or something in the center and a mass going around it, centripetal acceleration or force, the force is equal to a mass times velocity squared divided by its radius. Okay, in this case it would be from here to here. Okay, now this is a force, okay, and we do have a satellite that is going around, and it is at a distance r, and it has a mass. So what we can do, let's equate these two together. We'll call this equation 1 and equation 2 right here. So m v squared r is equal to m1 m2 divided by r squared. Okay, so this is what we're going to derive Kepler's third law from. Now, the first thing we need to realize, if there is an object or a planet that is rotating, it has a tangential velocity. Okay, we know from earlier on in this chapter that tangential velocity is equal to the radius times the angular velocity. Okay, we don't really care about that right now, but we need to know what the tangential velocity is. So if it makes one revolution in distance, and that would be in meters, that would be equal to 2 pi r. Okay, and if it took, what was the time it took to do one revolution? Well, that would be the period, so that would be t. So this is equal to v. However, we don't want this. We want to replace this v in this equation right here, because we want to get period, the t, into this equation. We're not going to be dealing with velocities, we're going to be dealing with distance and periods. Okay, so how do we do that? Okay, well, we have v squared is equal to 4 pi squared r squared divided by t squared. And so what we're going to do is that we're going to insert this equation right here into that right there. So let's do that. So that's m, sorry, yeah, that's right. Let's get rid of the m, because we have two m's, m on either side. So this becomes 4 pi squared r, let me use capital R on this one, okay, squared. So we have 4 pi squared r squared, and we have t squared. Okay, we also have an r on the bottom here. Okay, and this is going to be equal to the mass of the primary planet divided by r squared. Okay, so now we need to solve, make it a expression or equation that is going to look like this, that the period square is equal to 4 pi squared divided by the gravitational constant, and here should be the gravitational constant, times the mass of the primary planet, and all this times r cubed, and that is the distance of the satellite from the primary planet, from center to center. Okay. So this is right here in the center. Let me just say this right here. The 4 pi squared times the gravitational, universal gravitation constant times the mass. This right here is known as K, and that is Kepler's constant. And if you have a system, say the Earth-Moon system, then that will have its own Kepler's constant. By the way, for our planet, Kepler's constant, and this is Earth, is equal about 9.994 times 10 to the minus 14. No units. It's very small. It's a very small number, and it tells exactly, this constant, how everything should rotate, or masses, and what can change. It cannot just change on its own. Everything has its set period, and everything has its set distance from each other. Okay, and it's based on this constant. Now the sun and the planets have a different one. Okay, and if there was another satellite orbiting the moon, it would have a different Kepler's constant. Now, how we can also find Kepler's constant by taking the square of the period divided by the distance cubed of any, say this is the moon. Let's say this r is the distance from the Earth to the moon, and this is the period of the moon. Say it's 27.4 sidereal days. Okay, so you put that in seconds. put this in meters, and then you will get the Kepler constant for any planet. So if you were able to measure the period and measure the distance, you can figure out the Kepler's constant. In this case, we can look at it this way as the period square is equal to Kepler's constant times r cubed. Okay, I hope that was helpful. I have a video on Kepler's third law explained. Take a look at that one. That will go through more on some Kepler calculations and different strategies in solving problems.